Hello and welcome to the video portion of What Can I Simulate Choosing the Analysis Type. My name is Mike Fiedler. I'm a designated support specialist here at Autodesk. I'm going to walk you through today's presentation. So one of the things that we're going to do is open up an Inventor assembly, and this assembly you can see has quite a few different parts on it, and we can utilize different parts to take a look at different features within the simulation programs. And today I'm just going to start with one of the arms of the assembly here, and I will show you what analysis types are available inside the Inventor environment, and then we'll go ahead and take a look at how to set up a basic analysis. So I've already isolated that arm, and if you wanted to access some simulation from within Inventor, we can go to the Environments tab, and off of Environments I can choose Stress Analysis. And when I choose Stress Analysis and I say Create Study, you can see the Inventor Stress Analysis module here contains two different simulation types here. There's a static stress analysis type and there's a modal analysis type. In addition to those two finite element analysis types, you can also perform some shape generation here. That is to say that you can have the program determine what is critical material given the constraints, given the loads on the geometry, and I'll tell you potentially where you can remove material from the component that you have. We're going to go into the other analysis module or package that's here. If I go to Environments, then we're going to select Autodesk Inventor Nastran. The reason we're going to take a look at Inventor Nastran is because out of the simulation products that are available, currently this one has probably the greatest breadth of analysis types available. So as I come into the environment, you can see that we are set to a linear static. And if you wanted to change the analysis type, we can just double click. And then from the pull down menu where it says type, we can see there are all the different analysis types. So linear static, probably the most common analysis type that you're going to choose. You say I have some constraints, I'm going to apply some statically stable load on it, and I want to know what my deflections and stresses are from that. And then of course you have your normal modes if you need to figure out what sort of natural frequencies the structure would produce or react to. And then you have your buckling module. We have a number of different vibration modules. There's fatigue analysis available within Inventor Nastran. You also have heat transfer modules. So if you're going to apply some temperatures and say what does the thermal distribution look like, you can access those modules. And then at the bottom we have explicit dynamics and explicit quasi-static. So quite a few different analysis types, and by this point that you're viewing this video, you should have seen a few prior slides where we discussed in short what these different types of analyses can do. So if need be, you can always scroll back a couple slides and read those short descriptions on them. Let's go ahead and continue on with the setup to see how to do a basic analysis within Inventor Nastran for linear static stress. The first thing is each analysis that you do is going to need some basic components to that, and that's generally the material. You need to have some sort of constraints, you need to have some sort of loads, you need to have a mesh. And once you have those fundamental elements to it, then you can perform the analysis. So we can see that this particular component already has a material associated with it. It's a mild steel. If I wanted to change it, I can right click there and say edit, and I could type in values here in the fields appropriate to my material, or I could say select material, and then I could utilize the material library, either the Autodesk material library, the Inventor material library, or if I say load database, I can use the Nastran material library as well. So multiple different ways to get different sources of materials. I'm going to go ahead and say select material. We'll utilize something out of the Autodesk material library, and let's say that we change it to we'll scroll down a little bit further here. How about a steel ASTM, and let's take the A36. Okay, so you can see it reads in the values, and we'll just say okay. So now if I go back to the menu tree here, I can see that it has assigned the new material. So after the material, again, you need to have some sort of constraints, you need to have loads, and the mesh. So for the constraints, this end of the model is where the bucket was, and then the attachment points to the rest of the assembly were via these two holes here. So I'm going to apply my constraints here. And in this particular case, I'm just going to say that I need a constraint, and I'm going to change from a structural to a pin constraint, zoom in, select the surface that I want, and fix radial and axial directions and say OK. Now in a future module or a different module, we will talk more about loads and constraints. For the moment, we're just going to explore the basics of setting up an analysis so you can see what we'll say the minimum requirements are in order to perform an analysis. So let me go ahead and select pin constraint. I'll select that surface. Again, I'm going to fix radial and axial. Say OK. So now that I have some minimum constraints to keep the model statically stable, the next thing I can do is apply some load. So I'm going to tell it that I want to apply a load, select the surface, and then given that surface and the geometry that I have, let's rotate the model around a little bit. We're going to put it in the -y direction. So I'm going to say -10,000. And you can see here we're in metric, so this is magnitude of newtons. We'll say OK. All right, so at that point, I think the next thing that we can do is generate our mesh. So I can go into mesh settings. I can say generate mesh. That applies the mesh on the geometry. And then I can determine if that mesh is suitable or whether I want to go finer. Again, we'll have another module if you're interested in learning more about meshing and all the different controls that you have with meshing. So make sure to check that one out. For the time being, I'm just going to go ahead and reduce this mesh size, maybe about half. And I'll say generate mesh. And there we go. There's our new finer mesh on it, and that looks reasonable to me. So now we have basically the minimum requirements, right? We have the material associated to it. We have our constraints, the two different pin constraints that I added. And if you ever need to edit anything, you can just double click and get in and edit the constraints. I have my load. I can double click if I need to edit it. At that point, we're ready to run the simulation. So I'll just go ahead and say run. Pretty fast simulation. It's already complete. And then of course, I'm in the results environment and we can take a look at what the results of our analysis are. So by default, it's going to show me the stresses, again, in terms of a metric unit system. So that's megapascals. The minimum is about 0. And my maximum in this case is about 14, we'll say 15 megapascals. If I wanted to look at it in different unit systems, say the English unit system, I can go to the pull-down menu and select PSI. So I can see what that is. Maybe I need to capture some snapshots for somebody who wants to see it in English inch units. As I go to the pull-down menu here, I can take a look and see what our displacements are. And again, we're in terms of millimeters here. It's about 0.34 millimeters, which equates to roughly 0.0134 inches. So that is a little bit of an introduction to what different analysis types are available within the Inventor environment, both within the Inventor simulation and Inventor Nastran. Let's talk a little bit about changing it up. So kind of related to linear static stress perhaps is the nonlinear static, right? So if you have a material which is nonlinear in nature, or if you expect it to have rather large displacements, you might need to utilize a nonlinear static analysis. And I'll go ahead and show you how to set up one of those analysis too. So what I'm going to do is right click on my analysis here, and I'm just going to say duplicate. So this copies it into a new analysis. I'm going to rename this. We'll call it analysis 2 nonlinear. All right. And then again, to get into where the analysis type is, I just double click, and I'm going to go to the drop down menu, and at this point I can change it to a nonlinear static. Now for this particular analysis, given those loads that I just added to it, those constraints that I just added to it, you saw the results, right? So the results were relatively low stress and really small displacement. So there isn't necessarily particularly any reason that I have to go into a nonlinear static analysis for this. Just wanted to show you perhaps the differences between linear and nonlinear, and probably more so the similarities. One of the differences here is when I switch to a nonlinear static, we see that we have the large displacements. So it will account for large displacements and whether those loads are following the displaced geometry or stay in their initial orientation. So that's one of the advantages of nonlinear analysis. And then one of the other things is in the material. So when I go into the material, here in the material, what I can do is go down to the nonlinear button. So the other half of nonlinear analysis beyond just having large displacements would be the nonlinear materials, right? So I can go in and access nonlinear, and there I can tell it whether it's a nonlinear elastic. So I can define stress strain data points for my curve. I can go into an elastoplastic, and that would be like a bilinear curve. So you can see that we can define the tangent modulus past the yield stress. And so there are the fields where I can input these values, the initial yield stress, so it knows when that occurs. And then it needs to know what slope to follow once we pass the yield. And that would be defined by the tangent modulus, which can be input right there. So you could certainly do that as well. Maybe we'll do that. All right. So having chosen that material model, now you can see it says that the nonlinear material is on. So that way, if we were to apply a load and we exceed the yield, now it knows that it needs to start following the slope defined by that tangent modulus. At that point, I can go ahead and say OK. The other major change with switching to a nonlinear static analysis is that then you have to have some sort of nonlinear setup input. So on nonlinear setup, when I come in here I can define how many increments I want to have the analysis solve within. So in linear static stress, how it basically solves one analysis, it sets up the stiffness matrix and then figures out what our displacements and our strains and our stresses are. The nonlinear analysis is going to break this up into smaller steps. It's basically going to take your load, divide it up by X number of increments, and then come to a final solution whenever we sum up all those increments, if you will. So you can define what the number of increments are here, or if you leave that blank, you're basically telling the program that you would like to determine what you need. So I'm going to go ahead and just hit run. And there you can see that it's beginning to calculate through those different increments. And very shortly, there we go. The solution is completed. So there's my nonlinear analysis results. And again, because we were below the yield of the material, we can see that our stress has not changed significantly. And if we take a look at what our displacements are, we get the same displacement output, right? So you would only expect to see a difference in this if, with the linear analysis, the loads that we had applied would cause it to exceed the yield. In a linear static analysis, it would continue to follow the slope defined by the modulus of elasticity, whereas in the nonlinear analysis, once it reached that yield stress, then it would follow the new slope. But in this case, the loads that we had applied in both cases were below the yield of the material, so our results do not change significantly. Okay. Thank you for watching this video, and we'll see you in another one. Thank you.